So this stuck at 1, this stuck at 1, this stuck at 1. And for all three cases, output is going to be 0. And output stuck at 0, then output is stuck at 0. And now let us come to dominance fault collapsing. So this is equivalence fault collapsing. And now let us consider dominance. Now dominance you have to watch carefully. This is kind of easy to understand, but dominance we had to reflect for a minute. Let us define the term dominance. A fault alpha dominates fault beta if the set of tests for beta is a subset of the set of tests for fault alpha. So if the set of tests for fault beta is a subset of the set of tests for fault alpha, then we say that fault alpha dominates fault beta. And that means that for fault detection, and notice we are talking only about fault detection. If you simply want to detect presence of a fault, then fault detection, only the fault blank needs to be considered. Okay, what should I put in here in this blank? If fault alpha dominates fault beta, then for fault detection, we only need to consider which one? Said beta?
Alpha.
Alpha, you said alpha? But I thought you said beta before.
Yeah. I mean.
Okay, anyone else? Any different opinion? Well, I guess there are the two choices.
Beta.
Oh, so you changed your mind again? Okay. Yeah, I guess you have to think about it for a minute, because notice, okay. So it is, okay, let's consider this. Set of tests for fault alpha. Set of tests for fault beta, right? So, set of tests for fault beta is a subset, right? So here we can say alpha dominates fault beta. So if you want to detect a fault, alpha or beta, if you pick something here, it is going to test for both alpha and beta. If you pick something here, then it will test for only alpha and it will not test for beta, right? So you need, so your first answer was indeed correct. So, okay, so let's put here fault beta. So you only need to consider the dominated fault, right? And notice that this is only for fault detection. For fault location, and notice that the faults, if the test sets are disjoint, if the test sets are not identical, that means things are like this, then you can make a distinction between alpha and beta. And for fault distinction, that's a different issue. But if your objective is simply to do fault detection, that means if you have a unit, and if you want to know whether it has a fault or not, you don't care which one, then simply use dominance fault collapsing and test for beta. And if the result says that it is bad, you just throw it away. So let's look at an example. Okay. Here we have two faults, alpha and beta. And the set of tests for fault alpha and set of tests for fault beta. Now this is a simple example. Now, as I have said before, I'm going to keep examples simple because well, I guess right now we want to make sure that we understand the concept. And once you know the concept, then you can apply them to bigger circuits. Okay, what are the set of tests for fault alpha? This is stuck at 1. So anything that causes output to be 0 is going to be a test, right? So you have all the combinations that will look like this. Where X stands for a 0 or a 1. So basically all the combinations except 1, 1, 1. So this is actually a list of 7 combinations. Is that correct? Yes. 7 different combinations. And the test for beta, this is for beta. Line is stuck at 1, so you need to apply a 0 there. And in order to sensitize the output related to this fault, you need to make other two inputs 1. So this is the test. So we can say that tests for beta are a subset for tests alpha, and hence pick one of them. For example, 0, 1, 1. Oh, I'm sorry. I take that back. You have to pick only this one. There's only one choice. So 0, 1, 1 will test for both alpha and beta. And of course that will work if you are interested in fault detection. Okay, so if you so here this can further reduce the number of tests required, and if you use fault equivalence and dominance. Now there is a rather interesting theorem about fault collapsing. Now let's look at the idea of checkpoints. So here's a theorem, and the theorem says that if you have a now there are two related theorems, and let me write down one of them. First, in a fan-out free, notice we are saying this is true for fan-out free circuits, combinational circuit. Any test set that tests for all stuck faults, all fault stuck at 0 and stuck at 1 false at primary inputs. We'll test all stuck at false. In the circuit. Now this is a really nice theorem, right? It says that if you test for all the faults at the primary inputs, then that is going to take care of rest of the faults, provided it is a fan-out free combinational circuit. Now that is that's a severe limitation, right? Because most combinational circuits are obviously not fan-out free. So there is a revised version of this, and the revised version says in a maybe I can just revise this here. In a combinational circuit, this is the next theorem. In a combinational circuit, any test set that tests for all stuck faults at primary inputs and all fan-out points. Will test for all stuck faults in the circuit. Now both of these theorems, they have a proof, and it's not very hard, the proofs, but we are going to skip the proofs just to save a little bit of time. But this says that if you can test for all the faults at the primary inputs, and if you can test for all the faults at the fan-out points, then you will test for all possible faults in the circuit. So we can call these the checkpoints. So basically you test for faults at the checkpoints, and if you have done that, you have effectively tested for all the faults. Incidentally, we use this idea in software testing. So we came up with a scheme for testing software, and we came up with an idea called anti-random testing, which is opposite of random testing, and which can actually also be applied for hardware and software. But we, in one case, we applied it for software, and we figured out how to identify checkpoints in software, which is sort of a similar idea. Now, if you are trying to grade, let us say you are a TA or a professor, and you are trying to grade some homework or some quizzes, whatever, then one common technique is to look for some checkpoints. So if the student has gotten the checkpoints correct, then you can assume that he has gotten the rest of it correct too. So rather than checking every single step. So that's basically a similar type of idea as a checkpoint. Let's look at an example of use of checkpoints.